Traditional cameras capture the world around us in the form of a color image formed of red, green, and blue images. Hyperspectral images go beyond. They capture images at fine divisions in the wavelength, forming a three-dimensional cube of X, Y, and wavelength dimensions. While the applications of hyperspectral images are aplenty, scanning the whole hyperspectral image is a daunting task, as it needs to be done one spectral band at a time, or one row of the image at a time. How do we capture hyperspectral images rapidly without compromising on spatial or spectral resolution? We present SASSI, a super-pixelated adaptive spatio-spectral imager that can capture hyperspectral images at high spatial and spectral resolution at video rates. Our setup can image at more than half a megapixel spatial resolution with spectral resolution of 10 nanometers or better and at 18 frames per second. To see how SASSI works, let us dive into how images look like. The spectral content of a scene is often very complex. However, we do observe one thing. There are small spatial regions where color is approximately the same. It does then make intuitive sense the spectrum will be similar as well. Such spatially homogeneous regions are called superpixels that adhere to object and texture boundaries and provide a low-dimensional representation in the local neighborhood. How do we exploit this idea that the spectrum is same over a small area? Intuitively, it then suffices to sample at least one location within each superpixel. The spectrum at other locations will simply be a scaled version of this measured spectrum. We exploit this structure to build an adaptive imager that requires only a sparse set of spectral measurements. And fused along with RGB images, we can see that we can get very high resolution measurements. Our core contribution is in the form of an imaging setup that adaptively measures spectral profiles to the scene's properties. SASSI optical setup consists of two optical paths. The first path includes an RGB camera that captures color images of the scene. And the second path includes a spatial spectral sampler with programmable spatial mask that turns every single spatial pixel into a horizontal streak of spectrum. The SASSI pipeline proceeds as follows. First, the RGB or the guide camera captures a color image of the scene, which is then used to build superpixels. These superpixels are then utilized to generate a mask that is loaded onto the spatial modulator. This mask is created in such a way that no two spectral lines overlap. The grayscale sensor then captures a spatial spectral image of the scene's hyperspectral image, modulated by the spatial mask, giving rise to a sparse set of non-overlapping spectra. The sparse spectra are then fused along with the guide image to compute the full hyperspectral image, giving full spatial as well as spectral resolutions. All this just requires a single step, implying that we can achieve video rate measurements without compromising any resolution. Indeed, this allows us to capture high-resolution hyperspectral images with just one single RGB image and one single spatial spectral image. While a full scan would have required at least 68 images, SASSI required just two images, one RGB and one spatial spectral image. And the spatial spectral image was measured in an adaptive and sparsely sampled manner. This allows us to even scan very complex scenes, such as microscopic objects, without losing either spatial or spectral resolution. Such a fast and accurate hyperspectral camera is indispensable in imaging in vivo specimen, but dynamics of the scene plays a very important role. This camera also lets us scan very dynamic scenes, such as a live candle flame shown here, accurately at 18 frames per second. And SASSI captures the spectra and dynamics of the scene very accurately and very efficiently using as little as one image per frame. In conclusion, we proposed an adaptive hyperspectral imaging setup that starts by capturing an RGB image of the scene, which is then used to adaptively select sampling points. Spectra is then measured at these sample points in the form of a single spatial spectral image. This sparse set of spectral profiles is then fused with the guide image to form a full resolution hyperspectral image at video rate. Thank you.